mass for the top quark and the Higgs and so on. Okay, so this is the experimentally proved energy scale already, right? So now we know there's some reason to believe in the fact that this standard model is not sufficient. For example, the neutrino mass, the dark matter, and some theoretical thing, for example, how to cancel the quadratic divergence of the Higgs mass and so on. But there are reasons to believe in the beyond standard model. But unfortunately, we don't have any robust theoretical prescription which is consistent with the experimental result. So that's why the beyond standard model is completely a theoretical ball game so far. So this is beyond this electric symmetric scale. Now you can see that the different kind of energy scales are there, and there are different kind of theories are there. So the interesting part is it may happen sometime that the physics of two different length scales may not be connected to at all with each other. But what it may happen that okay, so the low energy scales, okay, maybe a sub theory of the high energy, and in a cascade you find out those kind of relations. And then if the scales are far away from each other, then this effective field theory would be a very good tool to explain or to understand those kind of scenarios. And that's where the effective field theory comes into the picture. So, and the modern era, why effective field theory is actually being very exciting because of this exclusion principles or the results from the experimental data. Because there's a beyond standard model, there are a lot of energies have been ruled out, and we have not found out anything. There's no any direct hint of this on-shell observation of some new particles. That means there's a desert regime starting from the electric scale to some few TeV. Okay, so and that scale may be enough to think about the theories at the low energy as an effective field theory. So yeah, so that's what I was talking about. What is effective field theory? It's a very good technique because it actually smells the presence of unknown physics even without knowing much, and that's the beauty of this effective field theory. And so what we have to do actually, we have to rely on the low energy theory, which, for example, for us as a particle physicist, it is like a standard model because we know almost all of the things about the standard model. So now we know that what is the symmetry, the space-time symmetry, and the gauge symmetry, the accidental symmetry, and so on, and what are the field content because we have observed them on shell. So now, based on these two things, what we can do, we can construct those effective operators, right? And that is what it is called the bottom-up approach. Bottom-up, in a sense, from the energy scale. You have this, low energy theories, and from them, based on that, you are actually constructing the effective operators. And we will discuss more on detail about this thing actually. Okay, and interestingly, this is the actually, the way the effective field theory was introduced. Okay, so that's why it actually captures the basic essence of effective field theory, where you do not have any clue about the new theory, but still with the low energy information, you can construct the effective field theory and try to grab the footprint of the higher theories and so on. There's another approach, which is basically called the top-down approach. And what it does actually, though it is considered the effective field theory, but if you think carefully or when you describe this in more detail, you will find out that this is actually more like an effective method to compute the full theory. So when you have a full theory at some UV scale, right? And then if you want to compute from the full theory, it becomes sometimes very clumsy in a sense because there are a lot of interactions, lots of particles are there. And not only that, because if you have two different or multiple different UV proposals are there, at that point, you cannot really discriminate them from each other, right? So then we'll see how this effective field theory can be a good handle to bring all those UV theories on the same platform, and we can perform a similar comparative analysis among them. So that's why the effective field theory has these two complementary methods. The one is bottom up and one is the top down, and you'll see that how this bottom up and top down approach we can use in a complementary way, and we can actually possibly proceed to address the inverse problem of the particle physics, that even if you find some kind of interesting result in the LHC or some other experimental data, how we can say that, okay, which models or which proposals are much more suitable to this compared to others. Okay. So this is more like a, the outline what I was talking about. So in the bottom-up approach, as you can see, there's a low energy theories are there, right? And then using some mathematical principle that I'll be talking about, you construct those effective operators. So that is how you want to capture the, the EV effects without knowing them in a detail. There's another approach basically from the high energy theory. You start with your favorite theory, okay, and then you identify what are your non-standard model modes or the particles are there, and if they are very far away, if they are very heavy, you can integrate them out, and then you can construct the low energy effective Lagrangian. This is a top down. But there's another interesting method which is more like favored for the experimentalist. That okay, as an experimentalist, sometimes when you fit different kind of data, you tell me, okay, let's see, there are few operators are there, and I find out there are some excess in those operators. That means that you need to explain some kind of new physics there. Now what you do, there is symmetry driven principle, and of course we'll be discussing about this in detail, that we can unfold that operator. Okay, so we have like a point like interactions, okay, and then you unfold that operator and then try to see that, okay, so what are the minimal non-standard model interactions you need to plug in such that you can get that operator. So it's like a reverse engineering of being from integrating out. So once you start with the UV Lagrangian, you integrate out, you get a 50 operator. But here we are asking a different question, that you start with the effective operator and then you ask the question, okay, what are the possible sources of the minimal extension of the standard model such that I can get this effective operator? So if you can learn about these three techniques, then more or less you will be handling effective field theory in a very useful manner. Okay. So this actually captures the ultimate goal that as an effective field theory community that we want to address. As I was saying, that okay, I don't know why the mouse tip is not working. Okay. So yeah, okay. So if you see, there's a renormalizable part, the IR theories are there, which is basically your standard model. Now you construct the effective operators, and then you get basically the big island, which actually contains all the effective operators. So, and this actually island you create order by order. For example, if you are restricted yourself to dimension 6, then you have a one island, there will be another island for dimension 8, and so on. So let's restrict ourselves for simplest one, the dimension 6. Okay. So from the bottom-up approach, you construct this island, and this island actually contains all the operators exhausted there. That means whatever be your theory at very high energy, and you just coming down, and actually it's very unlikely to go beyond this set actually. That's the superset of operators. So now what you do, that's the bottom-up approach construction is providing you this thing. Now you consider all the phenomenologically interesting extended standard model scenarios, and now what you do, you just identify the non-standard model particles. For example, here the capital phi j are basically my non-standard model particles. Now what I'm doing, actually I'm integrating out those non-standard model particles, and then I'm constructing an effective Lagrangian. And the effective Lagrangian now respect all the standard model symmetries. All the effective operators are basically constituted of those standard model fields only. That's all. So now you play the same game for different theories. So now you land on this bigger superset of operators as an island. Now it may happen that different theories leading to this subset of operators, there will be some kind of an overlap with those operators. That means two different theories which were initially looking completely different, but when you integrate them out, then you find out they are offering the similar kind of operators. Okay, and some of the operators are common, some of the operators are not in common. So that means if you assign some kind of experimental signature associated with those common set of operators, then it will signify that both or all the theories which give you that kind, those operators will explain that data. That means that there is a degeneracy in the theory space which you cannot actually further break. But it may happen that you can identify, okay, there are some operators which actually getting generated from this one or two theories, but not from others, and then you try to identify what are the experimental observers I can associate with them. Their positive result and non-result both will help you to understand what kind of new physics are biased with this experimental data, and that's how the this top-down approach can help. The another is basically what I was talking about the UV scenario. You start with the effective operators, you feed the data with respect to the experimental data. Okay, and then you try to understand what kind of new physics can explain that. So what you do actually, instead of having a blind hunch of this UV interactions, you unfold that operator, and then you gradually from minimal and then non-minimal and so on, you can understand, okay, so these are the three extensions, minimal extension I can perform, okay, such that I can get this operator at the low energy. That means that experimental excess can be explained by these three models, okay, right? So you need to perform some more experimental results to further understand, okay, among these three, okay, which one is the best, okay, and that's the level of precision and all those things, and all these things we'll discuss more precisely and more in detail. But so far, is there any question if you have?
Sir, I have a small question.
Yes.
In this slide, what are the G's signifies? The G1, G2, Gn, what is that?
Yeah, the symmetric groups.
Oh, achha, the symmetry groups. Okay. And the phi signifies the non-standard model particles.
Capital phi are the non-standard model particles, yes.
Okay. Okay. Thank you.
Okay, I suppose there's another question, so let me proceed. Okay, so let's have a look into this four Fermi theory and then see what are the lessons that we can learn from them. So let's start from the extreme left. So as you know, the muon decay was nicely described by this four Fermi theory. Okay, and you can see that the four fermion fields are there. So you can think of that as psi bar gamma mu psi, psi bar gamma mu psi. This is the, and if you are working with 3+1 dimension, each fermion field has a mass dimension 3/2. So this is like a four Fermi operator, or the four fermion field operators are there. So this is like a dimension 6 operator, right? So now at very low energy, or a few hundred MeV and so on, even the 1 GeV and so on, if you explain the muon decay and this specific channel, okay, using the GF, which is a Fermi constant, and you do not have any clue what is the Fermi constant, what you do, and you perform the computation of this cross section of the for this decay, and then you can adjust with respect to the experimental data, and then you get the value of this GF. But then what you can do actually, you can do now the higher order corrections to this process. And now you can see that another diagram is one loop diagram where you have a four Fermi interactions. And if you do so, then you'll find out this addition diagram, the quantum corrections to the four Fermi interactions, basically quadratic divergent. Okay, and so on. If you do more and more, it will be more and more divergent. Now, the interesting lesson that we learn from here, that actually the cross section increases with the energy. It's a clear violation of the unitarity, right? And then we realize, okay, so four Fermi theory is a good theory to explain the muon decay, but may not be true for all energy. It's restricted for some energy, right? So that means basically, okay, so this point like vertex may be, like effective operators. And as you know, the effective operators are associated with some kind of a energy scale, and we should not be close to that energy scale where this effective notion of this theoretical construction is invalidated. So GF, if you calculate the mass dimension of GF, is like a m⁻², right? And that's why there's a 1 by lambda square you can think of associated with the GF. So this muon decay through this effective operator, okay, is a fantastic way to calculate when you are far away from that lambda. And that is what the basic notion of the effective field theory. But this clear violation tells you that if you grow to the energy, and if you go more and more energy, at some point your theoretical descriptions will be far away from the experimental results. And that is why the violation of the effective field theory is actually, I would say, it's a good hint that, okay, there is some new physics is nearby your theory. Okay, so that if you grab that thing, then it will be a good idea to search around that energy scale. And the way it has been introduced is very similar to the bottom-up approach. You have in your theory, you have this SU3C cross E1 electromagnetism as a symmetry, right? And then you have the fields as muon, electron, anti-electron neutrino, and the muon neutrino. With them, you make a gauge invariant operator, which is a four Fermi operator, and that's how you capture this thing. So now there's another way. So if I have a four Fermi operator, so now if I want to unfold that operator, okay, what are the possible choices I can have? Now you can see through this unfolding, you can see there's some intermediate vector boson I can assign. That's like a minimal extension. That means you have a theory, and now you unfold that operator and you try to see what kind of UV interactions could be there, such that you integrate out those heavy modes, and then you get back your fourth Fermi operator. In this case, you can think of it like a W boson. You integrate a W boson, you get back this operator. So that's why the unfolding in a minimal way.
Jyoti?
Yes.
Yeah, just one thing. Apart from the quadratic divergence that you mentioned this in the higher order correction of this muon decay, what was the other point that you want to mention regarding this the diagram?
Okay, that the cross section increases with the energy indefinitely.
But that is true in the even in the first diagram.
Yes,
tree
that's
level-
the first diagram. So the
Yeah.
higher correction shows the failure of the effective field theory. One is the first diagram, the unitary violation.
Uh-huh.
Second one is basically the invalidation of the effective field theory because it's proportional to the cutoff.
Okay.
So the higher, that means the higher corrections you cannot treat as a perturbation.
Okay.
That's what it's like.
Mm. But then any higher order correction in any theory, forget about the effective field theory, they will have some cutoff dependency unless we renormalize them.
Yes, yes. So we'll so maybe I don't know whether I'll get the time, but there's a notion to renormalize the effective field theory. This is slightly different the way we renormalize the effect, normal quantum field theory actually. Okay. So it has to do order by order.
Okay.
For example, if I have to a dimension 6 operator, then I can renormalize the dimension 6 operator and I can calculate the beta functions and so on. But that will generate some dimension 8 operator, which I will be ignorant as long as I will restrict myself to dimension 6.
Okay.
Okay. Okay. So yeah. So now, so this is the one of the example that I was talking about, the unfolding. Okay. The fourth Fermi theory, unfold that, you get this basically intermediate vector boson, heavy vector boson. And now you can see that another way, top-down approach. Once you know, okay, you start with your theory, for example, the standard model is your preferred UV theory in this case. And then what you do, you draw this full theory diagram and you integrate out the heavy mode. So then you get back your fourth Fermi theory operator. And now the interesting part, that now you can see the slight difference between this bottom-up and the top-down is that when we talk about the bottom-up approach, we say, okay, GF is that dimension-full coupling I'm throwing. I have no clue about what is this GF. The only clue I can get what is the value of the GF after performing the fitting of this cross-section with the experimental data, right? But when you come with the top-down approach, now you know there's some, if you look at the UV diagram, in this case, there are some couplings. With the gauge coupling, muon, neutrino, and the gauge boson. And there's a gauge boson propagator, which contains this mass also. Now, that is, I expect there's some UV theory, there are some parameters are there. In this case, the UV parameters are gauge coupling and the mass of the gauge boson. So when I perform this integrating out, then I have this effective theory, I integrate out, I get the point-like interaction. So now if I perform the matching, so then what I can do, I can get the value of the GF. That's what the call it's matching actually. Okay, so that's what the matching is important when you have two different theories. Okay, and at some particular energy scale, you demand that both the theories are basically giving the same result, and that's how you do perform the matching as an order by order case. And also you have to remember this matching condition also depend on what kind of diagram you are talking about. I can have this same process in the standard model, which is loop induced. So then what that will do, it will change my matching condition through these quantum corrections. So then the GF will also have the contribution from these higher order corrections. So that's why the matching, we will see later when I talk about the matching for explicit cases, then it is actually like a matching at tree level, matching at loop level, or matching up to one loop level. So that matters. So one has to be careful when you perform, say that this is a matching condition, you have to mention at which order of the perturbation or which order you are doing that matching. Okay, so in this way, this is a nice example of the fourth Fermi theory from where we can get these three features, what I was talking about, the bottom up, the top down, and the unfolding of the effective operators to get back the basic knowledge, what kind of minimal UV theories it can have. Okay, so before proceeding further, so is there any question? Okay, so let me proceed then. Well, so this is the first thing that we'll be talking about. We have a low energy theory. and which we'll call the unified degrees of freedom. Okay, and then in the bottom-up approach, we'll construct the effective Lagrangian, and the Lagrangian initially we treat as a polynomial. Okay, and so first the construction will be more like in a classical way. So then we'll see how this classical polynomial things can be translated in terms of the covariant effective operators. So at this point, what are the important keywords that we should remember are the following. So we'll talk about the quantum fields, which are nothing but a representation of these particles. We'll talk about the symmetry, specifically the more representation theory. And whenever I talk about the dimensionality of the representations, that will give me the quantum number associated with the particles. And when I talk about the Lagrangian, it is nothing but for me as of now is like a collection of some singlet operators, which is a singlet under the all kind of symmetries I am imposing. It can be gauge symmetry, it can be some space-time symmetry, it can be some accidental symmetry. It depends on you what kind of symmetries you want to impose in your theory. And singlet implies that it's like all the terms are basically invariant under the each and every symmetries you are imposing. And what kind of symmetries we'll be talking about? We'll talk about the internal symmetries, which are either global or gauge. And I'll talk about mostly the internal symmetries, which are basically compact and connected. And then I'll have the space-time symmetry, which is basically non-compact. I will restrict ourselves for the discussion for the 3+1 dimension. Okay. So this is mostly like a Lorentz group I'll be talking about.
Just one thing, Jaydeep.
Yes.
Individual term in the Lagrangian being invariant under the symmetries, or individual term is singlet under the symmetries. The thing is that in supersymmetry, for example, where individual term may not be supersymmetry, where there is a cancellation under supersymmetry. So those kind of things will not be
okay,
then.
yeah. Thank you for this. So because we're talking about the effective operator, okay, and we talk about the mass dimension and so on. So automatically supersymmetry is excluded because supersymmetry you don't have the notion of the mass dimension and so on. That's a canonical dimension. But then the treatment of the supersymmetry is slightly different. But we'll be restricted ourselves for the only this non-supersymmetric.
Non-supersymmetric. Okay.
Yes. Yeah, because we will rely on the perturbation of the mass dimension order. Yeah. Okay. Yeah. So as we have learned that physics of different energy scale may be connected to each other or not. Okay. And then we have the two approaches. This is a summary slide. As the two approaches we have, one is the top down and one is the bottom up. And we have learned how what is the notion of this integrating out, what is the meaning of matching, and the truncation, as I was talking about, that where to truncate dimension 6, 7, 8 on this thing, depending on what kind of results you want to reproduce. And also we need to construct the composite operators based on the symmetry and unified degree of freedom. And one of the important and tedious tasks is basically not constructing the operators are not sufficient actually. Then you can write down two operators, okay? So these two operators may be related to each other by integration by parts. And why integration by parts? Because you remember, when you talk about the Lagrangian, it's actually the Lagrangian density. Now, when you write down the action, you write down basically the Lagrangian density inside an integral. Okay, so that's why evidently you can perform the IBP kind of thing, integration by parts, and you can connect to different structures with each other. So if two operators related to each other by integration by parts, we will not consider them to be independent. Okay. Similarly, when you construct the effective,
so IBP and total derivative, are they different?
IBP total derivative are different slightly. I'll just make a point on that too.
Okay.
And some point. Now, okay, so the equation of motion. So when you have this renormalizable part, okay, and then you basically construct, this renormalizable equation of motion of the fields. But now, when you construct the effective operators, then what you have to do, for example, if you are constructing dimension 6 operators, then you have to see the two different structures should not be related to each other by the equation of motion, what you have computed up to dimension 4 or dimension 5. Okay, so if you are working an nth dimension thing, then up to this nn minus 1th dimension equation of motion, you have to impose and then see, okay, these two structures are not related to each other or not. That's why the equation of motion is a constant that you have to impose. Now comes the total derivative. So the construction that we're talking about in a field theory, which is basically on the manifold, when there is no boundary. So that's why the total derivative terms, if the two Lagrangians are differed from each other by the total derivative, we'll consider them to be same. In particular cases, okay, when there is some kind of boundaries are there, specifically this kind of problem we can face. For example, when you talk about the integrating on fermions, and so what you do, we have to bosonize the fermion. Okay, now when you do these bosonizations of this fermionic field theory, then you generate some kind of boundary terms, even if you do not start with the boundary. Okay, so those cases one has to be very careful. But the kind of effective field theory we will be talking about in a manic quantum field theory in a manifold where there's a boundary, so that's why the total derivative terms will just drop. We'll assume they will die in the for the large surface and so on. So that's why I emphasize total derivative in a different way. Okay, so now before going to construction, let's see what is the low energy theory for us. So for us, when we talk about the standard model effective field theory, let's try to understand what is in the standard model. So in the standard model, we have this gauge group, which is SU3 color, SU2 weak, and U1 hypercharge. Okay, and then you have this quad, doublet, and singlet. Okay, and the right-handed objects that I have written, actually the conjugate of the left-handed objects, they are basically singlet. You have a Higgs doublet. Okay, and you have this different kind of gauge bosons, which basically extend the forces. And then, as I have mentioned earlier, that there is definite reasons to believe in the beyond standard model theories. So we can extend the standard model in a different, broad way. One, basically you may keep the symmetry part unchanged, right? And then you basically add new particles. Okay, for example, if you want to explain the neutron mass to type 1 seesaw, you have the standard model. You do not change the symmetry. You add right-handed neutrino, 2 or 3 copies depending on what kind of lightest mass you want. Okay, or you can add it SU2 complex triplet with some hypercharge +2. Okay, and then you get this type 2 seesaw mechanism neutrino mass generation. But also you can try to construct a much more complete theory, not just by extending your standard model symmetry, particle content. What you can do, you extend the symmetry itself. Sometimes, for example, if you want to accommodate Z prime, say, okay, standard model times U1 B minus L or something like that, or even the completely different theory, for example, left-right symmetry. You have a SU2L, SU2R, and then you have a SU3 color and U1 B minus L. And then you perform the another kind of stage of symmetry breaking to get the standard model. So these are broad 2 ways to do that thing, to construct this thing, beyond standard model. So now, this part we have seen already, that for the BSM Lagrangian, when we talk about the effective theory, so it is written actually the standard model Lagrangian, which is the renosal part, and we add on top of that the higher mass dimension operators, right? So now, in this way, we don't need to rely on what kind of UV theories are there. We are actually blind to that. We only rely on the fact that, okay, you have the standard model, the symmetries, and the particle content. We do not need any other information on that. So now, how does effective field theory appears here? So at the low energy, where you have this only the 4 Fermi theory and all those things, so that's the low energy effective field theory. So I'll show you some examples. What is the meaning of low energy effective field theory? But it's like a symmetry is basically C3 color times U1 electromagnetism. You have only the light quarks and the light, and you have the leptons, light leptons, right? And that's how you basically construct the effective operators on top of that to grab the picture on at the standard model or beyond that thing. Then you go a little bit further. Okay, then you have a standard model. Now, this standard model, if you integrate out this W boson, other gauge bosons, and the Higgs top, so basically you get an effective theory, and that effective theory is basically nothing but your low energy effective field theory. So if you come from the standard model, then you see in a bottom-up approach, the way you construct the effective low energy effective operator, that will be the superset, and standard model will offer you a subset of that. Now, if you go beyond standard model, then you can construct in a bottom-up approach the standard model effective field theory with your standard model symmetry and degrees of freedom, and then it will actually capture all possible BSM scenarios. But what you can do, you can start with your favorite BSM theory, you integrate out, and then you get a subset of the standard model effective field theory. That's why in a cascade way, at different energy scales, if they are different from each other, in a consistent way, and such that the effective field theory is validated at every scale, you can have a matching and description of different kind of effective field theories. So yeah, so this now in the bottom-up approach, as we'll add we'll learn how to add these higher mass dimension operators. Okay, and then while constructing these operators, there will be the independent set of operators are basically will be meaningful for us, and that's why we have to be careful about this implementation about the equation of motion and integration by parts. Okay, so now before jumping into the construction, let me discuss some of the subtleties in this construction. So the way we define the action is basically, as you can see, in the d-dimension as a measure and the space-time and your Lagrangian density. So if you work in a 3+1 dimension, so your Lagrangian density has a mass dimension 4, right? So now, if you look at the free theories, then you can construct the effective, mass dimension of those quantum fields, and that's how basically get the scalar field, gauge fields, the spin one, and the field tensor, and the Fermion field, and the covariant derivative. Here, because we want the construction to be, in a coherent way, and also the construction is such that we don't need to check the gauge invariant separately. So instead of having a normal derivative, what you'll do actually will introduce a coherent derivative. So that's why this coherent construction will automatically ensure the effective operators that I'll be writing, but automatically the theory Lagrangian will be gauge invariant. Now the question is basically, okay, fine. So are all these quantum fields will participate in an operator construction? The tentative answer is yes, but if you think carefully, that we do not consider the gauge field explicitly in the operator. The gauge fields are basically masked within the covariant derivative or in the field stem. And the reason is basically if you write down the gauge field explicitly, then it becomes very tedious to be consistently write down a gauge invariant theory. You may miss out some term and checking the gauge invariants and so on. So gauge fields are not actually directly participating in this construction. Their representatives are basically my covariant derivative and the field stem. So that's why when I'm talking about the operator, so this operator will contain my scalar field, the Fermion field, the covariant derivative, and the field stem. And that's the reason here I have defined the operator in this particular form. So you can have a P copies of phi, you can have a Q copies of psi, and you have a R copies of D and S copies of field tensor. Now this Q by construction of the invariant is basically your Fermion field cannot appear alone. So it's like a psi by psi. So Q is always even integer. So now if you look at the mass dimension, then the operator which actually written like this, having a mass dimension of P plus 3Q by 2 plus R plus 2S. And this is the operator mass dimension, right? So now you can see that if you change the value of P, Q, RS, you can generate the same D. Right, so there's a degeneracy in the D having defined values of P, Q, RS. And that's what is an important thing in the effective field theory. And that's why in a given mass dimension of the operator D, you get different kind of structures. Okay, so that's why you might, okay, so you can have a P equal to D, but that means basically all my effective operators consist of, phi only. Similarly, you can
field tensor can also be written in terms of the covariant derivative.
Field tensor also can be written on covariant derivative, but this covariant derivative, what I am writing, the different definition, the difference is X is basically commutator of d mu d nu. Okay, but these D are the free D, which will be act on the fields. Okay, that's why the D and the X are written separately.
Okay, but you'll anyway have various different Ds, right?
Sorry?
Or if you have various representation of let's say of the groups, different fields, let's say transform differently under the various representation, you will also need to have various covariant derivative.
Okay, so I'm not answering in detail, but as you have raised this question, in the construction, D, I'll have only one D. Now, what you're saying that Ds are defined at their soul. That means when I unfold the D, then the inner structures will be defined based on D is acting on which field. Right? But when we write down the operator D, we write down everything as a D. For example, if you write down a Lagrangian standard model Lagrangian, we write down just d mu phi, d mu phi. We write down psi bar d slash psi. We don't write down d1 or d2.
Okay.
But depending on what is the psi, and we could do that because D is not transforming under the internal symmetries. The internal symmetries actually playing more role for the phi and the psi. right?
So,
And
so
then,
what you are saying is that mu means doesn't enter in this all the mu's, various mu's. They do not
yes,
enter in the Lagrangian directly,
yeah,
but we have a different field strength tensor to take care
yes,
of
field
its.
tensor and the D.
Okay, yeah.
So when you unfold the D to calculate the Feynman vertices, then you will get back those your A.
Okay.
Okay. Yeah. Any other question? Okay. Okay. So let's see that another kind of symmetry that is important. Here the space-time symmetry. And for 3+1 dimension, we have the Lorentz group. Now the interesting part is the way we'll construct, we need, the information that we'll be using is very much true for the compact group. Now the space-time symmetry here is a non-compact, so I cannot directly use this information. So what I'll do, I'll work in a SU12 plus SU2R in that way, and you'll see more why on that thing. For example, which is like more like a wild representations. So my scalar will have a J1, J2, which is 0, 0 because it is completely scalar. Now left-handed fermion will transform as an SU2L doublet, and these are the SU2R singlet. This is like a half, 0, and vice versa the psi r. And the covariant derivative is like a bidoublet under this space-time symmetry SU2L plus SU2R. And similarly, field tensor is like a left-handed, right-handed is like a 1 and 0 and 0 and 1. So these are the yes.
Yeah. To make the Lorentz group compact, why don't we just Wick rotate and demand side reflection symmetry from the theory, and then if that theory is fine, then the counterpart in the Minkowski spacetime, that theory will also be fine. So can't we use that logic?
No, actually we do that, and that's the way we get basically SU12 plus SU2R. Okay, so SO4C is like a complexified your SO4. Okay, and the way SO4, if you see in that way, the way we'll construct this thing, those representations are not exactly the representation of SU12 plus SU2R. So that's why we cannot do that that way. You need to extend the Lorentz group to something called the conformal group, and you have to do that thing, and I'll possibly discuss something about that thing also. But yeah, but that will not work immediately on that way. That will be insufficient to do that thing.
Thank you.
So now, for example, let's say now you have on top of that you have a gauge symmetries, right? And then you have this phi, psi, and chi. So these are the quantum numbers. Now you see how the symmetries are playing a role. If I look at the space-time symmetry, then I could have written down phi 5 as an operator, right? So like 5 to the power 5 is a Lorentz scalar and the dimension 5, fantastic. But this is not allowed by the internal symmetry. So this is not allowed. So that's why. So the idea of constructing these operators, basically, you just use the symmetry as a filter. You start with the Lorentz symmetry and you find out what are the possible Lorentz scalar at given mass dimension you can write down. Okay, you write down all of them, and then you see, you assign the internal symmetry quantum numbers to those fields. Okay, and then see are they invariant under the internal symmetries or not. If they are not, you just throw them. So that's why having the same space-time symmetry, the invariant structure that you got, basically we call not the operators but the operator class. Now having individual operator class, there could be different kind of operators which are allowed by the internal symmetries. That's why inside a operator class, I can have a multiple operator. For example, if you think about, there's a renormable part also. Think about the standard model. So for me, the operator class is like a psi squared D. That means an operator consists of the two fermion field and one covariant derivative. Okay, but if you now know what are the psi you have, all these psi's are there. So you'll find out, okay, there are some ER bar D slash ER, LL bar and D slash LL, all the operators. But actually the operator class is psi squared D. So that's the discrimination we do actually. We first think about for a given mass dimension, what are the operator class? Now within an operator class, what are the operators which are allowed by the internal symmetries? And that's how we get the operators. Okay. So one more example, what I was talking about for the standard model. For example, if you write down the UCOS sector, QL bar DRH, now you can see it's like allowed by the internal symmetries. So it's perfectly fine. And then one can introduce a Smith interaction, which was like QL bar gamma mu, tau are the basically your Pauli matrices. The two currents are there, and you just basically J mu interactions are there, and that's basically allowed by the SU3, SU2, you want individually they are singlet under the symmetries, and it's a Lorentz invariant. So this is an allowed term in my Smith interaction. But if you calculate the mass dimension, this is a dimension 6 operator, so you can write in dimension operator. So now the question is basically, if I could write down this way, then what is the harm? The harm is that there are so many fields, there are so many symmetries, and on top of that, I have to be careful about the the integration by parts and equation of motion, those kind of constant. So it is very tedious to do them by hand actually, right? Because that becomes very clumsy and erroneous. So we should come up with a very consistent mathematical prescription to construct those operators, and that's the prescription I'm going to talk about now. Yeah, but before jumping into that, is there any question?
Yes, sir. Could you just kindly redefine how are we preparing this operator class? And from, I mean, I got the point that from the operator class, how we are choosing the operators on the basis of which are invariant under the local symmetries or not. But how are we preparing this operator class? How are we choosing that? Could you just redefine that once?
Yeah, so basically the operator class, if you see, the way we have written down this operator O as a phi P, psi Q, and this thing, this actually give you the operator class for different choices of P, Q, RS for a given D. That's all.
So permanent all those all the different combinations of P, Q, R, and S will give us a large variety of operators together, which we are referring as the operator class.
Yes, there's the operator class, and now different choices of psi, phi, X will give you different operators within the same class.
Yes, and from these operators, those who are invariant under the local symmetry, we only choose them, and we reject the other ones.
Yes, yes.
Okay.
Is there any other question? Okay. So now let's, for the time being, keep aside the notion of the quantum field theory, fields and particles aside. We'll come back to that. But let's talk about the very classical way. For example, I can think of a series, okay, which is more like a monomial basis, because x square, x cube, that thinking like a monomial basis. Okay, it's like a polynomial, which you can write down like a 1 plus 1. You can think of like x to the power 0, x1, x square, and x cube, and so on, right? And then I can have two variables, x and y. So I could write down some more terms like x plus y, x square plus xy plus y square, and so on. So here, in the language of operator and operator class I was talking about, if you think about, like, for example, if you think of order 1, where order 1 is basically order 1 polynomial, where you have a variable appears only one time, right? So in the order 1 polynomial, you have two terms, x and y, okay? And now, in the order 2, you have x square, xy, y square, and if xy, if you do not allow them to commute, then yx. So now you can see the fourth term. Now you can see, if you go more higher and higher order in the polynomial, okay, you will have more and more terms. And that's what we encounter in the effective field theory also. If you allow your Lagrangian to accumulate dimension 6, dimension 7, dimension 8, and so on, you have more and more operators there. Okay, so that's why we have to come up with this mathematical principle to actually calculate in an exhaustive way. So now, you have a standard model Lagrangian, and then you basically adding those more and more higher dimensions, which is like equivalently adding more and more order of the polynomial. So then, how do you catalog, perform this cataloging of this invariant polynomial? For example, if you have a scalar field, okay, so then you can write down like a phi square, phi cube, phi 4, phi 5, and all those things, okay? And then you allow, okay, I have phi and the covariant derivative both. So I can write down d square, which is a Lorentz scalar, and then d2 phi, d4 phi, d4 phi square, all those things. Now, when I'm writing all the possibilities, I am not careful about the the redundancies. For example, if you write down a d2 or d4, those kind of total derivative terms, or d4 phi 2, even a total derivative term, or d4 phi, okay, will be ignorant as of now. If you have only fermion fields, you can write down psi square, psi r square, or this kind of terms. If you have a fermion and scalar, then you write down those kind of terms as well. But once you impose the internal symmetries, then you can see from these structures, the phi, phi q, phi, phi, these operators are absent actually. Okay. And similarly, you can write down a psi square phi and psi square phi cube classes and psi square phi square. These are the classes are basically allowed. So in this way, the different kind of symmetries actually playing in the complementary role for this filtering. So this is the chart that I was talking about, that once you increase the number of dimensions, if you allow the number of dimensions of the operator mass dimension to be more and more, things become more and more complicated, and that is the reason we need an algorithm. Let's try to understand the algorithm. First, let's start with the complex scalar field, which have just the U1 symmetry, and the is the abelian symmetry. So phi is going to the power I theta phi, and its conjugate goes as to the minus I theta phi star. So you can write in a possible invariant term phi star phi to the power n. So now one of the invariant term you can immediately check for n equal to 1, because under this term U1 transformation, your phi star phi is invariant, and so the phi star phi whole square, phi star phi whole cube, and so on. So all any integer power of this phi star phi is basically invariant, and that's why you can write down this series of invariants like h as a 1 plus phi star phi whole square, and so on. Right? These are all possible invariants actually you can write down. Now this series actually you can recast in terms of very nicely in an integral form. Okay, which for example this series is equivalently writing 1 by 2 pi 0 to 2 pi d theta by 1 minus phi e to the power I theta times 1 minus phi star e to the minus I theta. And now what you do actually, you introduce a unimodular complex number, which is your z, or z equal to your writing as e to the power I theta. Then you can write down the closed contour integral, okay, with a unimodular z mod z equal to 1, and dz by z 1 by 1 minus phi z times 1 minus phi star by z. And if you expand this denominator, then you'll find out, okay, fantastic. So I can write down exponential of minus log of first term and the second term, and then I expand the log series. Okay. At this point, I do not worry about the convergence and all those things, because I know that there will be some kind of mass dimension once I introduce that automatically takes care about the convergence, because I want the convergence in terms of the mass dimension or the mass dimensional couplings. Okay. So I'm not worried about the convergence of the log series at this point. So this is a nice way we can represent this integral in this exponential series. Okay, and if I calculate this residue theorem, then you'll get this thing. Why? Because if you see, this is a nice way the whole h can be rewritten. It's a unimodal. It's like a complex integral about the unit radius circle, and then dz by z. This is basically your integration measure. And there's a special name, it's called the Haar measure. I'll come to this thing in details. You don't need to be confused at this point. And then the exponential part is there. The whole exponential part has a special name. It's called the plethystic exponential. And inside the exponential, that is called the generating function. Now, why this is called the generating function? Okay, so if you think about, if you are familiar with the path integral formalism, it is actually, if you write down the Euclidean path integral, exactly similar structure you'll get from here. And in a layman's language, you can think of, okay, there's an exponential part of this thing. Now, if I expand this exponential from this argument, what it will do actually, it will write down all possible combination of phi and phi star. Now, interestingly, you will get some of the structures, which is like a phi square phi star, which was absent in my earlier h when I write down the invariant term. So this generating function actually generating all the possible combination of phi and phi star, with being blind whether it's invariant or not. Okay, and then once you expand that, this is what you get actually. You get basically the first 1 plus this thing z to the power 0 term, then z to the power 1, then z square, then z cube, then 1 by z, and that terms. Okay. Now, if you can recall your residue theorem, then you'll find out that the 1z is basically sitting here in the Haar measure dz by z. So whatever you are getting from the exponential argument independent of z, that will only contribute, because that's what associated with the simple pole. So that's why the first term is basically if you fit in the Lagrangian, it will be dz by z the first term, right? So that is the simple point. So that is the non-zero conclusion from the residue theorem you will get. All the terms will not become zero. So that's why this integral, once you perform the integral, you will get back whatever by hand you have written the invariant term. Okay, so now you may be wondering, okay, so is that the only way to pick up that term? What happened if I say, okay, so I want to pick up some other terms? Yes, you can do that thing. So what you do actually, you want to, let's say, include this phi plus phi, phi star phi in the second term. Then you multiply that by divide the Hermezar by the coefficient of that z, and that's how you reduce the residue theorem and brings here such that you pick up the second term. Okay, and that's become the invariant, and this will be important. The reason is basically sometimes from the invariant series, if this U1 is not a gauge symmetry but rather a global symmetry, and you want to pick out some of the operators which actually violate the global symmetry by some unit, right? Then, for example, baryon number, electron number, you have the standard number, you write down the standard number thing, and you want to have what are the operators that break standard baryon number by this amount of q unit. Then what you'll do, you just write down z to the power minus q, and you write down the whole exponential part, and then you project out only those operators which violate the baryon number. And that's how this is the minimal way set up where you can see that how an invariant polynomial can be written in terms of some integral, a complex integral. And that is the sole part of the whole construction. Yeah, so I think this may be new to many of you. So if you have any question at this point.
Sir, in the last part where you were defining that if we wish to introduce some other parts into this polynomial, this series part, so could you just re-explain that part? Like, why do we need to reintroduce the other parts? And like, I don't catch the.
No, I don't need to introduce that part. If I want to have operators which violate my E1 quantum number, that means basically when you write down a term in the Lagrangian which violates some baryon number or lepton number, okay, then your Lagrangian is not actually completely invariant under that symmetry. Okay, so but
obviously, right.
This method gives you, if you know what is the amount of violation, okay, you can scale that amount of violation through this Z, okay, and you project out those operators which violate that global symmetry by that amount. So this technique not only give you the invariant quantities, but also you can project out the operators which violate the global symmetries. That's the case.
Acha. Okay.
Okay, any other question? Okay, so yeah. So
Jaideep.
Yes.
Jaideep.
Yes.
Hello. So, for example, the thing that you were actually saying, let's say there is some baryon number violating operator. Okay. But for example, let's say this in this expansion, if I look at the coefficient of z, there are several operators inside that. All of them will be baryon number violating, or only maybe all of them. Okay, yes, so then you have to just multiply by z inverse.
Exactly. Yeah.
Okay.
So what get actually
that all of them will be baryon number violating.
Yes, but that implies that in that theory you get similar amount of baryon number violation at different mass dimensions.
Okay.
So what I'm saying, in the standard model, you can write down the baryon number violation by 2 units, let's say. But you can get violation by 2 units at dimension C, dimension 8, dimension 10, also. No? So you get all the operators in different mass dimensions. You may truncate at some point, depending on your choice. Okay. But the similar amount of violation occur at different dimensions. That's what I'm saying.
Okay. Now I'm just saying, let's say the part that is multiplied by Z. Okay, so it's not clear why all the operators will be then. Maybe it's that, let's say, all the baryon number violating operator at that dimension will be multiplied by Z, but then there can be other operators also which are not barrier number violating, but still are coefficients coming as a coefficient of Z? Is it not possible?
No. So let's say if I say that okay, my E1 charge is basically 1, okay, the second term, all the operators, phi times phi star phi, because phi star phi is an invariant quantity. So phi times phi star phi, that violation is also 1 unit.
Okay.
Okay, phi
Acha.
times phi star phi whole square, because phi star phi is an invariant, so the violation is basically linear in phi.
Okay, I got it. Yeah.
Right, but what they are doing, they are increasing the mass dimension of the operator. If you see,
Yes.
that's what I'm saying. The order of the violation is 1 unit. But they are appearing in a defined order of the polynomial.
Sure.
Okay. Is that
Okay,
answer?
thank you.
Does that answer your question?
Yes.
Okay. Fine. Yeah. Any other question? Okay. So with the simplest example, within U1 case, we have done this thing, right? So now, okay, this is a nice thing to start with, but this is not all you can understand, because I mean, we have to reach till the standard model effective field theory. So let's recapitulate what we have done. So we have started with the fields and their conjugate fields, and we can write down the platistic exponential. We have the symmetry information. That symmetry information also goes in the platistic exponential. And here you can see in the exponential platistic exponential, there are two kind of variables are there. One is basically phi and phi star, which are more like a classical variable, like a spurion kind of thing, which are not quantum in nature. Or I'm not talking about the commuting and non-commuting. It's like more like a Grassmann kind of variable here. Okay. And this Z are like a coordinates. This is like more like a unimodular. So if you think about the, S1, if you want to parameterize in terms of theta, so either you think about it in terms of e to the power I theta, or you think about it's like a coordinate system is basically Z. Right? You can describe by that thing. That's like a coordinate. But coordinate of what? That we'll learn soon. Then we have to introduce, when you perform the integral, complex integral, there's an integral measure is there, and that's the invariant measure is defined in case of U1, we have identified dz by z. Okay, but this happens to be like dz by z here. We do not know how we should write down the hard measure. So there should be some prescription to calculate the hard measure. Okay. And once you have this platistic exponential and the hard measure you glued together, then you basically construct that integral from the polynomial that is called the Hilbert series. So we have see how for a given abelian symmetry you can write down the Hilbert series. So now next task basically in which cases we can generalize this Hilbert series. Okay, so we have to understand what is the Z as I explained and how to generalize this construct. So what is this Z? The Z as a parameter e to the power I theta, right? So this is like a unimodulus circle. So now you can think of this E1 is a representative of your maximal torus. Okay. So what you have to, so maximal torus, so how to do that thing? So if you start with a connected compact group, then it will have a corresponding its maximal torus, which you describe by a Tn kind of thing. And you can think of this Tn like n copies of U1. Okay, so for example, if you think about, let's say, SU2, okay, so SU2, what is the rank of the group? It's a 1. Okay, so that's why its corresponding maximal torus will be T1. Okay, if you look at for the SU3, its maximal torus will be T2, but this T2 I'll be writing as a U1 times U1. Now every U1 actually will be parameterized by one of this e to the power I theta or Z. So that will tell you that how many Z coordinates you need to introduce. So number of Z coordinates is equivalent to the rank of that group. For example, for the E1 is a abelian. So it's only one. Its rank is one diagonal generator, so it has only one Z. SU2 is also rank 1, so SU2 maximal torus coordinate will be only one Z. For SU3, rank is 2, so it will have two such coordinates, Z1 and Z2. And what are those coordinates and how to do that thing we'll learn little later. But now, when you write down Z to the power 1 or Z to the minus 1 and so on, so this Z to the power Q if you define, where Q is basically +1 and -1. And that's how you introduce some kind of polynomial function in Z, which you call the character. So the ultimate thing is basically to calculate the character function of this in terms of the torus coordinates. So that for the abelian case, the torus, the character functions are very simple. It says z to the power q, and now it depends on your what is your assignment of the q charges. It will be like if your charges are plus and minus, the character function will be z and z inverse. If your charges are plus 2 minus 2, it will be z square, z to minus 2, and so on. So we need to learn that, okay, for abelian case, E1, we know how to calculate the character z to the power q, but how to calculate the character function for the other groups, especially the non-abelian groups. So this characters for a given group is basically like a trace of this irreducible representations. So this is like abstract definitions, and this is not very useful for the computation. So we'll translate this language in terms of more working knowledge. So how to do that thing? So here, so how to do that thing? So for each symmetric group, we have to identify what are the symmetric group, whether it's a internal symmetric group, whether global or a gauge or space-time, whatever, right? But we have to remember that this construction, we can do this character computation only for the time being for the compact group. So we'll talk about the compact groups only. And boson and the fermions, they are different from each other because fermions are anti-commuting in nature, bosons are commuting in nature, right? So for the boson case, we introduce the statistics as a exponential series. And if you see, this is very similar what I introduced for the previous example when I talk about the scalar field in the E1 case. So exponential series, you write down phi to the power r, chi r, which are the basically function of the z divided by r, small r. Now, what is this chi r? Chi r basically your character functions. We yet do not know how to calculate them. We'll learn about that. But what we know that these character functions are basically the function of this torus coordinate, which are basically z. And what is this phi? Phi are basically like a Grassmann variables here, or like more like a spurion. Okay, they are thrown in my statistics just to trace the presence of the quantum field, because initially we get a group invariant polynomial, and then we'll identify this phi, presence of phi, chi, d, and x, and from there we'll translate them in terms of the covariant form. For the fermion case, the situation is very similar. In this case, phi is the fermion, but because of their anti-commuting in nature, that is taken care of by the addition factor of -1 to the power r plus 1. And the chi r and the z are represented basically exactly the same thing as the character functions. So, in this construction, the first thing we need to know how to calculate the character functions for a given fields, okay, depending on what kind of symmetries we have. Now, why the symmetry principles are important and robust? That internal symmetries, if you think of, for example, for the standard model, you have SU3, SU2, and U1. If you forget about the space-time symmetry part, okay, they do not treat your different spins in a different way. That means if you have a SU2 doublet, the way you write down SU2 doublet of a scalar field, you write down the SU2 doublet of Feynman field in the same way. It's a two-component object. You have a triplet, you have a three-component object, and so on. So if I rely only on the internal symmetries, these internal symmetries will not discriminate your spins. Similarly, the computation of these character functions also actually relied on the algebraic part of the groups. They do not discriminate what kind of spins they are. That means the character of a SU2 doublet scalar and the character of a SU2 doublet fermion would be the similar. So that's why when you calculate the character function, we will be blind to the fermion. Will rely mostly on the representation theory, and just looking to the dimensionality of the representations of a group, we should be able to write down the character function. Later we can say, okay, so this is a fermion field, this is a scalar field, this is that. But the character functions will be remain unaltered for different spins particle. If their representations under the internal symmetry are same, their character functions will be the same. That is one of the important tasks. important information in this context. Any question? Okay. So now, yes.
Sir, just one small question, which may be a very lame one because I might have missed that portion. Are you defining the fermions and bosons together as spurions?
Not two, they are basically introduced in as a spurion.
Acha. Okay.
At this point, I am not adhering any kind of quantum measure of the fields. These are classical construction.
Okay.
Okay. Any other question? Now, what?
Just one thing. This
Yes.
also includes gauge bosons also.
Gauge bosons are basically, yes. So phi is a representative of D and the X.
Okay.
X because they are the bosons.
Hmm.
For the D, we will introduce as a fermion later. Yeah. But D is slightly different. We'll talk about how this D is introduced. Yes. But F mu will be part of this phi. Okay. Okay. So now, as I'm saying, the life is not so simple because we do not have only one symmetry. You have a product of symmetries. So then this construction will be extended for the product of symmetries. So then for individual groups, okay, so you have to construct you have to identify what are the representations. For example, if you remember, for example, let's say quad doublet under SU2. So these are, and they are also triplet under SU3. That means they have the SU3 charges as well as SU2 charges. So then when I'm writing the character functions, so I have to write down the character for that field, which is basically character of a SU2 doublet times the character of a SU3 triplet. So that's why they are just the product of this thing. And why I can write down the product? Because these two groups are the direct product. They are independent to each other. If they're independent to each other, their torus coordinates are also independent to each other. That's why one of the coordinates is a y and the coordinate is a z. So if you have a n number of independent groups and you identify the representations of a particular field under that n number of symmetries, and for each representation, you write down the character function and you take a product, and that's how you get the total chi. If you follow the steps, it's the simplest one. So now, if you have multiple spurion, like for example, if you have two scalar fields, okay, and they are transforming on two different symmetries. So you calculate for the phi one for two different symmetries as I mentioned earlier. Similarly, you do the same thing for the phi 2, and then in the exponential, you just add them. Because they are the polynomials, they are the classical variables. There is no commuting or anti-commuting behavior here. They are taken care in the polynomials. Polynomial is like a scalar quantities. So that's why you don't need to worry about whether they commute or not. Those are the classical variables. You just add in the exponential things and you just keep adding them, as many fields you have. And that's how you get the total statistics. That's all. So let's recapitulate what I have told now. So you start with the spurions. And you have the information of the symmetries. Depending on the symmetries, you identify what is the maximal torus. And from the torus, you just calculate that using the torus coordinates, the character functions for those representations. And also using the torus coordinate, you write down the Haar measure and those character functions and the spurions, you glue them together to calculate the Plathistic exponential, and the Plathistic exponential and the Haar measure join together to give you the Hilbert series. So that is the simplified flowchart how these things actually work. And the construction that we will learn, we'll try to see that how minimal information we have to provide such that I can get maximal output. So now it's the minimal information that we should provide the information that we have. That means basically at the low energy, what are the information we have? We have the information about the symmetries. We have the information about the fields. That is the input, right? The symmetry and the spurions. That's all. And the algorithm we should construct in such a way that this should act as a black box. We don't need to give input at every point. This will be taken care of in a cascade way. And at the end of the day, this program should give you the Hilbert series, which is nothing but the invariant group symmetry invariant polynomial, which I can translate in terms of a Lagrangian. That's all. So that is the whole idea behind this construction. So let me tell you what are the details about this program. So the program that I'm talking about, so it's actually considered basically the connected compact group, okay, and then it automatically translated in terms of maximal torus, and from there you can construct all those structures. Only thing, the representations of the fields, you have to mention about the dimensionality or the linking diagram, and from there it can calculate anything. So we'll see how this works. Okay, so yeah, so this is the one slide about the SUN. I think I have mentioned already about the SUN. So it's like a special unitary. So it's the determinant is 1. These are the traceless generators, and the dimensionality is n square minus 1 because we have n square minus 1 number of generator. Rank is n minus 1. So that many torus coordinates we have. So that's the information needed. Yeah. So before I proceed further, any other question? Okay, so let's now try to see that how you calculate the characters.
Just one more thing. We
Yeah.
have 5 minutes. So
Okay, we have 5 minutes. Okay, I think then it is better
yeah,
to
we can
stop
take some
here
questions.
because yeah, this will take some time and this thing.
Yeah.
Yes.
Maybe we can have some questions and then we can.
Yes.